So we're streaming now. Let me double check everything and make certain we're live everywhere. Let's see. All right, so I'm up on Facebook. All right, let me double check on Periscope. Hopefully that's working. Let me see, have I got my mic going? My mic's going. I'm on Periscope. Hello, good morning. Good morning, guys. So I'm on Periscope. Looks like I'm on YouTube. So what are we doing today? Have you guys been paying attention? Do you know what we're doing today? Those of you who voted on the polls, guess what? We are going to talk about dark matter and dark energy. How exciting is that? I'm pretty excited about this. I have done a short before. Good morning. Good morning. So I have done a Science Minute Monday when I was doing those back in the day. Really short version talking about dark energy. But today we are going to talk about both dark matter and dark energy. Woohoo! How exciting is that? Are you guys excited? I'm really excited. I got to learn some new things about this. So let's go ahead and get started. If I can get my video. Here we go. Howdy. So today we are going to talk about dark matter and dark energy. So this is pretty interesting because there's so much unknown stuff. And hello, good morning, afternoon, and evening, wherever you are in the world. It's morning for me, so we have Saturday morning science here at ScientistMel headquarters. And if it's afternoon or evening for you, happy afternoon, evening, science, Saturday or Sunday, whichever day it is for you. So what is this dark matter and dark energy? All right, so dark matter makes up about 27% of the universe. Now, we do see an expansion of the universe as accelerating. Dark energy is about 68% of the universe, and the thing is, only 5% of what we see, 5% of what we see is this normal matter. So you're looking around, we see the earth, we see everything around here, we're like, hey, that's just 5% of the universe. And so we're still trying to figure out what the heck is this dark energy, this dark matter, all of this stuff. So I have a really cool kind of graphic here, and so I'm going to kind of discuss this. Hello everyone. So what is this really kind of groovy thing going on over here? Well, what this is kind of explaining to us is this shows the changes in the rate of expansion since the birth of the universe. The more shallow the curve, the faster the rate of expansion. So this curve changes a lot about 7.5 billion years ago. So right around here, about the 7.5 billion years ago, we go from, you know, this little boom to like, and it just accelerates rapidly. So it's okay, guys. Happy Saturday. Hello, everyone. So if you're asking who I'm talking to, oh, and if you're new to this, we are also streaming on Twitch. I'm interacting through here. I'm talking to people on Twitch, on Periscope, on YouTube. I don't have the Discord chat going on here right now, so I have to fix that. But the Discord chat will be up and available when I start my Hey ScientistMel 24/7 stream. So I'm actually also broadcasting on Facebook. So I'm broadcasting on several different platforms right now, and fortunately through Restream, I'm able to get everything. So, oh, CCO Gamer says to come here. Well, tell CCO Gamer thank you, and I'm so glad you guys are here. So if you're curious, what's going to happen this weekend, I'm adding more shows to my Hey ScientistMel 24/7 live stream. I'm going to incorporate all the chats together, and so that live stream will be going on 24 hours a day, 7 days a week. It'll be like a TV channel to where it's all of the science content put together in particular blocks. You like my Batman shirt? So all of my science content will be put together according to content blocks. And so, hey, TV don't even do that, do they? No, they don't. And so I'll have all my videos all together, and I do want to incorporate other content. I had internet issues last weekend, so we are relaunching it. Can I say something about earthquakes? I can put earthquakes on. So if you're curious, so let me kind of give you guys a little bit of rundown since we got some new peeps here. So over here, you will see some chat going on when I go onto this screen, and you'll be able to see what everybody's saying to each other and saying to me, which is kind of useful. So what I'm going to do is the 24/7 live stream is going to happen. It's going to start this week, and it'll go throughout the week. And the only time it'll pause is when I'm actually live streaming with you guys here. But the cool thing about the 24/7 live stream will be that I will be able to pop in the chat, and you'll be able to pick whatever block you want to watch, because you'll know when it's coming up, because I let you know in these little miniature videos. I'm like, up next we have such and such, and here's all the content. And so that way you can hop on and you'll be able to interact. And if I can't get to your questions right away, I will most definitely get to them as soon as I possibly can. But that'll give you an opportunity to just kind of have science going on in the background wherever you are. So how cool is that? 24/7. Yeah. So let's hop on back on target. So what we're talking about today is dark matter and dark energy, Mel 24/7. Yes, and I do want, and I'm reaching out to other science communicators because I want to incorporate their content as well. So if you know anyone who wants their science content kind of boosted on a 24/7 live stream TV version where you can tap in anytime you want, it'll be on Twitch, it'll be on Periscope, it'll be on YouTube. Can't quite get it to work on Facebook just yet. So, hey. So, you should put the Peggy 18 to enter. I don't know what PEG is. I'm totally not I'm not down with the cool kids and all of the jargon. So my apologies. I kind of live under a rock because I'm all about the science. So there you go. Okay, so as we're looking at this particular graph here, we can see that we have this huge acceleration of expansion compared to the slowing expansion. And so this curve changes a lot about 7.5 billion years ago when objects in the universe began flying apart even faster. They're just like, oh my gosh. So astronomers, they theorize that the faster expansion rate is due to all of this mysterious dark force that is pulling galaxies apart. Dark energy. Am I right? Dark energy. So who first coined this idea with dark energy? When was the Earth born? I believe it was the Big Bang's around 15 billion years ago. Let's see. We can go back to the previous graph. Oh, the Earth was born, it was about 13 billion years ago. Around that. Not the universe, but the Earth. Around 13 to 14 billion years ago. So, Einstein first realized that this empty space in the universe is not nothing. Because when we look out in the universe, we see these stars, we see things like this, and you're like, wow, look at all the stars. What's all this black space in between? He was the first one that kind of stepped up and said, there's something there. I'm so smart. I hope so. I have 4 degrees, but this is what I used to teach. So really quickly, my background, because I'm new on Twitch. I have a Master's of Arts in Teaching, specialized in secondary science education. I have a Master's of Science in Analytical Chemistry. I have a Bachelor's of Science in Biology and also in Biochemistry. I'm currently in industry science. I'm trying to get a little bit of experience there. I've performed cancer research as well as genetics research, so it's a lot of fun. This is a project that I'm doing because I feel like scientific literacy is extremely crucial right now. And so I'm trying to make all kinds of science accessible to everyone. Can I come? I would love to come to your city and explain these items at your school, and I am available to do that. If you want that information, you can hop over to ScientistMel.com, and that would be awesome. So Einstein was the first to realize that this empty space is not just nothing. There's a cosmological concept that kind of shows that it possesses its own energy, and energy a property of space, and it would not be diluted as it expands. Now, Einstein was the first concept, but the observation of galaxies drifting apart, that's something else altogether. You live in Terracina. You live in Italy. Well, Italy would be pretty cool. We can get that to work. Now, this empty space is full of what we call these temporary particles. They continually form, and then they disappear. Now, physicists tried to calculate how much energy they have there, and they got a very wrong number. Do I personally have any speculations on dark matter and dark energy? I don't have any particular speculations. The thing is, this isn't necessarily my field, but I do like learning about it. And the thing is I'll get into detail about what they think makes up dark matter. And if you're like, oh my gosh, where did you get all this information? Fear not. All of my slides are available on ScientistMel.com. The last slide always has all my sources. You can download my slides and dig in a bit further for yourself, and you can be like, you know what, ScientistMel, I'm going to need your evidence. Well, I'm a scientist, and I'm happy to provide that. So physicists couldn't quite quantify this. They tried to calculate how much energy was associated with that, and they got a very wrong number. Because, you know, science is 90% failure. And the failures kind of give us a general idea of what direction we need to go. So what they thought is like maybe dark energy is dynamic. It's like an energy fluid or field. And it fills space, but is opposite to matter, okay, and normal energy. So it's not what we see in normal energy. It's not normal matter. It was named quintessence, the fifth element, of Greek philosophers. And so there's no clue on anything about it. So we're all still like entirely gobsmacked, befuddled, and like, what the heck is this? But they're trying. They know it's there. Hello, everyone. Hello. Oh, here we go. So let me go to this. I don't expect you guys to read giant books. Those are actually my notes. So sometimes I get this thing going on where I accidentally pop over, and I was like, oh, hang on now. So let's talk a bit about Einstein. Einstein might not be correct in his theory of gravity, because the theory of gravity by itself with relativity affects expansion in normal matter. Galaxy and cluster behavior give us examples of that. But there's new gravity theories that might be needed for these motions of bodies with the current theory, but there's nothing compelling that can refute Einstein's relativity right now. And it's quite, that's why we have special relativity. So until we better understand dark energy and its effect, the fifth element, Lulu multipass, right? I should get a multipass. And so until we understand a bit better what's going on with dark energy, the theory of relativity and special relativity is the best thing we have right now. So what are the possibilities of dark matter and dark energy. So what could dark energy be made of? You're like, what the heck is this about? Well, could be a property of space. Could be a property of space. It could be like a dynamic fluid. Or we would need an entirely new theory of gravity in order to incorporate dark energy into the equation. So this is kind of a, let's see, not big monitor, this way. All right, so this is kind of what scientists have had to say. Scientists have found, and so this is kind of, this comes from NASA. Scientists have found that an unexplained force is changing our universe, forcing galaxies farther and farther apart, stretching the very fabric of space faster and faster. If unchecked, this mysterious force could be the death of the universe, tearing even its atoms apart. This kind of sounds like a sci-fi film, doesn't it? Dark energy. The revenge, you know, I don't know. It's just, it sounds kind of, it sounds very ominous and scary. But, you know, the expansion of the universe is accelerating. We have dark energy as 68% of the universe. And it is a complete and utter mystery. And right now, all we have to go on is Einstein's theory of relativity, special relativity, as well as gravity. It works well right now. And we don't have anything to refute it. And so until we get better with, the doctor will say this, hey, I got my little mini TARDIS right here, you know? It's just, it's cool, man. So, but, you know, until we have a better grasp and understanding of what actually dark energy is, especially in regard to the properties. Is it a property of space? Is it a fluid? Is it a dynamic fluid? Do we need an entirely new theory related to gravity, especially when we incorporate it into the parts of space that we have a hard time seeing? It is called dark energy because it's dark. It's not visible to us in the best ways. So, the net results of the virtual particles. Here, I'm getting some questions, so I'll pop this up over here. So the net results of the virtual particles, if these are conserved, then the positive input must come from a neighboring cosmos. Maybe. That's a possibility. So it's hard to say. But there are things that they're looking at in regard to dark matter. So how about we switch gears and talk a bit about what dark matter is. So I've already mentioned a little bit about what dark matter is. I haven't talked much yet. So dark matter makes up about 27% of the universe. The rest, everything on Earth, everything ever observed with all of our instruments, all of our normal matter, adds up to less than 5% of the universe. So this begs the question. It's called dark, and I'll tell you why it's called dark in just a second. This begs the question. So if dark matter and dark energy, dark matter and dark energy make up the majority of the universe, and we're just 5%, maybe we're the ones that are the weirdos. You know what I mean? Why are we called normal matter? Maybe the normal matter is everything else that doesn't make sense to us. Perhaps that's the normal matter, and you know, we're the oddball strange matter. That might be a thing. But hey, so what is dark matter? What do we think about it? Well, we are more certain about what it isn't than what it is. It's called dark because it is not in the form of stars or planets. So the stars or planets that we see, these are the visible forms of matter. So if we can't see it in these visible forms, we call it dark. I, for one, have often been called a weirdo. I'm a weirdo. I'm pretty certain I'm a weirdo. But hey, that's all right. Yes, we are the minority matter exhibits. This is an accurate statement. We are the 5% matter. We are. People, everything you see, everything that you know, the stars, the planets, everything that's observable, as vast as that is 5%. 5%. The billions and billions and billions and billions and billions of stars and, you know, all the stuff that we see, everything is just 5% of the universe. So we are all weirdos in our own right, so it's okay. We're the weirdo matter. So we're certainly, why would we be the normal matter? Who wants to be normal? That's not as exciting, because that's where all, you know, hey, we're the weirdo matter. So what is this matter we're talking about? Oh my goodness. All right, so I'm going to talk to you a little bit about what dark matter is. There is too little visible matter that we see to make up this 27% of matter we have in observations. Now, it is also not in a normal matter form, but possibly made of particles called baryons. You know, keep dark and baryon, you know. I really think we need stickers like that, you know, instead of keep calm and carry on. Keep dark and baryon, B-A-R-Y-O-N, so baryon. Oh, goodness. So if it were in some sort of cloud formation, we could detect it by how it absorbs radiation. So we know these baryons are not in a cloud formation. So contrary to what some think, dark matter is not antimatter. You're like, well, is it antimatter? No, because it lacks the distinct gamma rays that are produced from antimatter and matter colliding, and so this isn't observed. We don't see any of these collisions happening with where dark matter is present. We also know that it isn't galaxy-sized black holes. Baryons are normal matter. So, but we know that dark matter could possibly form made of particles called baryons. So we can see that dark matter is present in specific things. But sometimes it's absent. Sometimes you have weirdo galaxies where dark matter is absent. You're like, what the heck's going on there? Which poses more questions, which is actually okay. We also know that it isn't galaxy-sized black holes because we do not see enough of that lensing associated with matter bending near black holes to account for all of that 27% seemingly invisible matter. So if you're not familiar with lensing, I'm going to talk to you a little bit about how that is a means of detecting certain types of, essentially the effect of gravity on light. Because we know, Einstein told us and showed us, that even light cannot escape gravity, which is actually kind of pretty cool and scary to a degree. So here I've got the various things that dark matter could be comprised of. Yes, those are the particle theories of dark matter, such as WIMPs. We are going to talk about machos and WIMPs and axions and baryonic matter. This sounds kind of like it could be a really cool song. You know what? We could come up with like a cool song about dark matter just from these groovy, we could almost do like Village People-esque type of songs with machos, machos, machos. I got to be a dark matter macho, something like that maybe. So, dark matter could be baryonic matter if it was held in brown dwarfs or in these heavy chunks, or these densely packed chunks of heavy elements. Now, these are called massive compact halo objects, or machos. Not nachos, but that kind of makes me hungry a little bit because I like nachos, but machos. The common thought, though, is that dark matter is not baryonic, but made of particles like axions or WIMPs. What are WIMPs? Weakly interacting massive particles. So they have weak interactions between each other, and they interact and these particular things are massive particles. Dark matter is nachos. I think that would be awesome if dark matter was nachos. Machos with cheese sauce. Do not forget the jalapenos. You know what? I wonder if dark matter is the nacho cheese sauce that holds the universe together. Wouldn't that be awesome? If the nachos themselves were like the normal matter that we see, is the nacho cheese and the jalapenos collectively working together to make our universe tasty. Dark matter. I don't see primordial black holes as a possible candidate for dark matter. Probably not, no. All right, so let's talk about machos and wimps. Machos and wimps. We'll look at the flow patterns in the pic. So if you're not familiar, we got Wimpy right here, and we got Popeye. Popeye protests to be macho, and Wimpy, you know, he's wimps, but hey, that's all right. If you've not checked out old school types of cartoons, you got some homework to do. Apparently spinach makes Popeye strong. So let's talk a bit about machos and wimps. And just so you guys know, I know this isn't my field, but this is a lot of fun for me to be able to talk about stuff like this. So I'm glad you guys voted for this. Now I want to preempt all of this stuff before I just start laying it on you. NASA has a fantastic website that is chock full of information in regard to dark matter and dark energy. And some of the graphics that I used, I pulled from that site. And all of the information that I'm giving to you right now can be readily found on the NASA webpage. So I'm kind of just breaking it down for you in little bite-sized pieces, because I find sometimes just explaining things is a bit easier than going through and reading lots of information. But, 'cause NASA, that's right. And so if you haven't had a chance, you can go to my website, click on ScientistMel.com resources, download the slides, and just dive right in all of the nasty yummy goodness of machos and wimps. So, what are machos? Well, they have lots of different sizes, and they can go anywhere from small, teeny tiny stars to supermassive big holes, big black holes. They are made of normal matter and can be black holes, neutron stars, brown dwarfs, and we've already mentioned brown dwarfs as a potential for holding dark matter. Now, what makes all of these massive objects, black holes and neutron stars? Do you guys know? Supernovas. So supernovas of massive stars generate these massive freaking objects. Now, a neutron star is about 1.4 to 3 times the mass of our sun. Now, black holes, however, are 3 times the mass of our sun. So these are pretty freaking huge. Can they hold dark matter? Well, the upside. Since neutron stars are huge, and if they are isolated, they both can be dark. So you can have this dark matter there. You can have stuff that, you know, doesn't formulate and become visible. Now, a downside, supernovas are not terribly common. And since they're not very common, we don't have the formation of a lot of these massive freaking objects. And because supernovas are massive and they should at least generate a huge amount of energy, as well as these massive objects, they should also generate these heavy frickin' elements. However, there is no evidence currently that they occur in enough numbers within the halo of our galaxies in order to fill that 27% dark matter qualification. Hypernova. Hello, everyone. Brown dwarfs, though, they have a mass that is less than 8% of the sun. And so if we find dark matter in brown dwarfs, they're a lot smaller, and so we're trying to meet that 27%, you know what I mean, of dark matter in the universe. They're so much small. They're less than 8% of the mass of the sun. So they're tiny, comparatively speaking. So there would have to be a lot of brown dwarfs to be harboring dark matter. What about primordial quasars? Oh, goodness. What about primordial quasars? From what I've read, I haven't read anything about primordial quasars having anything to do with dark matter. Black holes vary in size. It's the Schwarzschild radius that dictates how matter collapses into black holes. All right, so what do we do to detect machos? This is where we get into lensing. So using these gravitational effects on light from distant objects, we kind of revisit Einstein here with his experiment in showing that light cannot escape gravity. You know, he discovered that this gravitational attraction of a massive object can bend the path of light. So this is kind of similar how a lens works. So when you have a massive, massive, ginormous object that passes in front of a distant object, like a star, a galaxy, you know, big freaking planets, you know, the light from the distant object is focused. Now that object appears brighter for just a teeny, tiny, tiny short time. Now, they search for these machos. They usually are looking for brown dwarfs in this case, in the halo of our galaxy by checking out this brightness of stars near the center of our galaxy and stars in the large Magellanic Cloud. I say words wrong sometimes. Magellanic Cloud. So there you go. Hello, everyone. So if you're not familiar with this particular project, ScientistMel knots. There's a particular project called the Macho Project. Woohoo! And this is a group that uses that type of lensing technique that I was talking about, where they have objects pass in front of each other and then they're able to see that light get a bit brighter for a short period of time. They've observed about 15 of these events over the course of 6 years. They set a limit as 20% of the contribution of dark matter in our galaxy due to the objects with the mass lens that 0.5 of that of the sun. So that's kind of cool. Words are hard, Jay Garner. They are sometimes, and I stumble over them. And I'm willing to admit that. Sometimes my brain is like going do really, really fast, and my mouth does not catch up. It's a weird thing sometimes. You will tell your nephews about my show. Yay! Thank you, J. Michael, for hopping on. So, astronomers, what are the pros or the upsides associated with machos? Well, astronomers have seen these objects that are either brown dwarfs or large planets around other stars using these properties of this lensing technique, these gravitational lenses that they use to detect machos and this sort of thing. Now, the downside, well, they have observed, astronomers have found no evidence of a large enough population of brown dwarfs that would account for all of the dark matter in our galaxy. So, as I mentioned before, since supernovas are so freaking rare, we don't have them terribly common. We don't have a lot of these things going on where you could hold a lot of dark matter. They're going the route of brown dwarfs. They just haven't found enough brown dwarfs to account for that percentage of dark matter. Such is life. Now we're on to WIMPs. WIMPs, weakly interacting massive particles. So if you're not familiar with what weak interactions are, I'm going to explain that to you. They don't form covalent bonds or solid bonds. They just kind of interact weakly with positive and negative charges. But they're massive particles. And so WIMPs are the subatomic particles that aren't made up of ordinary normal matter. They are weakly interacting because they can pass through ordinary matter without any effects. So if they were strongly interacting, then you would have these particles attaching to various molecules in your body or other forms of matter, but they just weakly interact. So there's no permanent change to any kind of molecular structure. So that's good, I guess. Now, they are massive in the sense of having mass. Whether they are light or heavy depends entirely on the particle itself. Now, these particular candidates that we are looking at include neutrinos, axions, and neutralinos, covalent bond. That is the chemist talking in me. Hello, everyone. Hello. I'm so glad you guys are enjoying this, and I'm super glad you're here to enjoy Saturday Science with me on the Science Hub. Neutrinos. If you're not familiar with neutrinos, I'm going to give you a little bit of history. And again, all of this information I'm bringing to you comes from NASA, and you will have the links on my site, ScientistMel.com, under resources. Neutrinos were technically kind of invented by physicists early on in the 20th century because particle physics is hard and they needed some kind of particle to make sense of these interactions. So sometimes you're like, there's got to be a thing here that makes the other things work. We'll just call it neutrinos for now. Well, guess what? Later on they were discovered. And physicists and astronomers had a good idea how many neutrinos there are in the universe. They were thought at first to not have any kind of mass. However, 1998, one neutrino was discovered to have a particular mass. Now, neutrinos are very, 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 very small. So the mass of this particular neutrino was exceedingly small. The mass is too small, though, for neutrinos to substantially contribute to any kind of significance in regards to dark matter. Glad someone is scoping about the real science. Yay! I'm so glad you're here for that on Periscope. So, axions. And I believe on an episode of Cosmos in the first season, Neil deGrasse Tyson went to Japan and there's a neutrino detector where you sit in a boat inside of this particular channel, and it's like it's a cylinder, and there's this water there. It's pure water, and you're sitting, I believe it's water. Believe the solution is water. So and it detects neutrinos, and when it detects a neutrino, the whole room lights up. It's absolutely amazing. It is so cool. All right, so axions. They're particles that have been proposed to explain the absence of an electrical dipole moment for the neutron. So axions, okay, if you're not familiar with what a dipole moment is, that's positive and negative charge on opposite ends. And so axions were kind of generated to kind of explain why there's an absence of that on a neutron. Now, they would have been produced abundantly in the Big Bang. Current searches for axions, and they're trying really hard to find them, involve laboratory experiments, as well as searching the halo of our galaxy and looking for them in the sun. Ice cube to detect neutrinos. I bet that's cool, man. So we're currently talking about WIMPs. We've talked about neutrinos. We've talked about axions. And so we've talked a little bit about the issues associated with those. Now let's move on to neutralinos. That almost sounds like a cookie, doesn't it? I kind of want to eat a neutralino. Sounds like it should have like some kind of hazelnut or chocolate in it. I don't know why. Like lady-fingered neutralinos. Can you tell I'm hungry? So neutralinos are members of a type of set of particles, and they were proposed because you notice the underlying thing here. Sometimes scientists have to propose a particular particle in order to get the math and the science to work. And so they're like, well, we have to have a thing that interacts with these other things in order to make these things work. And so then they are like, well, this makes sense. It has to have these particular characteristics in order to get these things to interact. And then later they find it. So that's always quite, but it takes a long time. So neutralinos were kind of proposed as part of a physics theory called supersymmetry. Now, this particular theory attempts to unify all of the known forces in physics. Neutralinos are massive, being that they are 30 times to 5,000 times the mass of a proton. Now, given that's not massive to us like an elephant, but when you're looking at, saying, okay, here is, I've got like, it's, I got a little teeny tiny, if I got like a little dust particle and then I got my huge freaking light up D20, that's kind of massive, so many references to food. Yeah, I really want cookies now. That's entirely my fault now, huh? So hungry from all that sciencing. Thinking takes up a lot of energy. You want to clean my house? It probably needs it. All right, so we're looking at this particular neutralinos are huge compared to protons, up to 5,000 times the mass of the proton. But they are the lightest of the electrically neutral supersymmetric particles. So it has no charge. It's considered neutral. And so what do astronomers and physicists want to do with that? Well, they're developing ways of trying to detect these neutralinos underground or in searching the universe for signs of their interactions. All right, so the upside for this. Well, technically, there is a possibility that these very massive subatomic particles, if you have the right amounts and with the right properties in the first moments of time after the Big Bang, are the dark matter of the universe. These particles are also inherently important because these scientists seek to understand the nature of subatomic physics. And so the underlying theme here is we made up these particles in order to get the math to work. And then we found out they're real. So that's kind of how it goes. So a lot of this generating of, well, we have to have neutralinos, we have to have neutrinos. And we're kind of seeing that also with dark matter and dark energy. Sometimes you have to come up with the concepts. What is dark energy? Is it a superdynamic fluid? What makes the math work? And so you have to go with that aspect. And then you go and you're like, okay, now that we know that this makes the math work, let's start to try to detect it. Now, what's the downside? The neutrino. It does not have enough mass to be considered crucial for dark matter. And so far, observations have not been able to fully detect axions or neutralinos. Reverse the polarity of the neutron flow. Oh my gosh, you're like, hey, you can't reverse the polarity of a neutron, it has no charge. Those are the things that make me nuts as a scientist. Reverse the polarity of the neutrons. You're like, there's no polarity on neutrons. You don't have a positive or negative charge, so you're just like, ah. Oh my gosh. So what does that leave us? Here we are, back with the machos and the wimps. I don't know, wimps seem pretty cool in this scenario. So what are the other factors that scientists can use to determine between machos, wimps, what is it for those components of dark matter? So there's results by the WMAP satellite showing our universe is made up of only 4% ordinary matter. So maybe there's a bit less matter than, normal matter that we see than we thought. This seems to exclude that large component of machos. So about 23% of the universe, that would then make it about 23% of the universe is dark matter. Now, this favors the dark matter being made up of mostly some type of WIMP, whether it's neutrinos, neutralinos, or the axions. That's shifting towards that. But this particular evolution of structure in the universe indicates that dark matter doesn't move very fast, which would be kind of problematic because we know that the universe is expanding rapidly. All right, so since fast-moving particles kind of prevent clumping, because it's just the universe is going to bits, right? We don't see this in the universe. So while neutrinos might be part of dark matter. They're not really a major component. So what we've got to go on at this point is axion and neutralinos. They appear to have what it is that makes sense in regards to the needed properties in order to make up dark matter. But yet, we can't find them yet. We don't know where they are. We haven't been able to detect them. But the properties that they exude make sense for dark matter. If the neutrons are flowing, there would need to be a larger amount in one place flowing to a place with a lesser amount. That was always me guess making Doctor Who science work. So wrapping up a little bit here, we have the expansion of the universe accelerating, which is one of the forms of evidence for dark energy. And dark energy makes up about 68% of the universe. Dark matter is 27%, but trying to find this dark matter in regard to the amount of it has been very, very elusive, and it's a complete and utter mystery right now. So it kind of makes things a bit difficult. You're like, hold on now, you know, what are we going to do here? So I have a typo on the next slide. So that's exciting, just to show you guys. I have a typo on the next slide because, you know, the K is really close to the M, darm matter. So here's all my sources. And so I'll post these on my website for you so you can kind of check that out. And you'll be able to go on scientistmel.com/resources and see these for yourself. And always feel free to ask me questions here. Darn matter indeed. Yes. Darn. It should be an N. Darn matter? Gosh, you know. How funny is that? Yes, you know, typos are a thing, and it's always fun sometimes to have a typo and see who notices it. So darn matter indeed. So please do check out my website. Bo's been posting the links to it. It's real easy to get to. There's all kinds of information there just for you at no charge, of course. If you can help me out, that's great. So I'm going to take a moment to thank my super awesome patrons. And I believe and I've added Sarah on here. Sarah's the latest. And I've got Paula stuck up at the top, so I forgot to format this for this slide. So let me say thank you so much to my patrons on my patreon.com/ScientistMel. Tony, James, Lauren, Jen, Carl, Melanie, Patrick, Daniel, Stephen, Paula, Tim, Carrie, Cersei, Keith, Zachary, Tony, Bo, Sarah, Graham, Dragnot, Godless Iowan, Jennifer, Corey, and Heavy. You guys make what I do possible. I'm able to, I have new lights because of of their contributions. I have a website. I have a new camera. I just got a new desktop. It's refurbished, mind you, but I only just got the desktop. I already had a monitor and a keyboard. I'm going to start doing the hashtag HeyScientistMel 24/7 live stream all the time. All of my content, unless you're using a laptop, yeah, no charge. So if you can, buy me a coffee each month. It's just $1 a month for pledges. I'm working on developing a show just for my patrons, exclusive on my patreon.com/ScientistMel. It is just me who does this. And so I often rely on the kindness of others to help me do what it is that I do. And I do have a few friends like Peter, Gonna Go For It, who makes all of my intros. Tony, Doc Hack and Slash has done music. So it's ScientistMel TV, Hey ScientistMel 24/7. So you'll be able to watch all of my shows anytime you want on a constant live stream and get to see what other people are talking about. You can find me everywhere on the internet. I'm also on Twitch now. So those of you who have been watching on Twitch, this has been awesome, and I thank you for that. Thank you. You know, people do Periscope on dark matter and cosmology. We'll recommend you to them. Thank you so much. I appreciate that. And so if you're unfamiliar with what I do, and I am on Discord, and that will also be for ScientistMel 24/7, Discord, Twitch, Periscope, in YouTube, all of those chats will be in a form kind of like this here. So it'll, I believe it's kind of set up like this. And so when you're watching Hey Scientist Mel 24/7, you'll have your picture and you'll have your video in the center.
Hi, ScientistMel here. I wanted to take a moment to tell you a little bit about this account.
Which is
I
really,
have
really,
4
really
degrees.
cool.
3 of them are in science.
So you'll be able to see what everybody's having to say about that and be able to interact in that way, which would be really awesome. And so that's going to go live, I believe, tomorrow. I had internet issues, and so the initial launch was just like, yay, it's going. And then it just went, and I'm just like, well, that's just great. Thank you, internet, for going out. And so rather than having constant, now we're up again, then we're down, now we're up again, I wanted to make certain I worked out all of the potential issues in advance before I go live again with that. So there you go. So if you haven't already subscribed, check me out on YouTube. Ask me questions there. I'm happy to help in any way that I possibly can, help you understand the content. And all of my topics are viewer generated. I don't pick what it is I talk about every Saturday. I also have other shows called Spirited Science, where I sit around with a bunch of people and we have an adult beverage, a cocktails that's based on the content that we're talking about. I'm going to start having local live streaming from local venues at pubs, bars, breweries, and get them involved so that we can also incorporate the general population in local areas and hopefully traveling around there. What is the meaning of life? The universe and everything. 42, is it not? 42? 42. So look for that, because we'll be raising money for charity as well as research organizations as well. And if you don't like the live streams, that's okay. We have ScientistMel Shorts, which are shortened versions of the longer streams. So you have that available, and little minute videos here and there. So I do lots of different things, and they're all organized according to playlists on YouTube. So you can just go and find the one that you like. So thank you guys for being here. This has been a super fun stream. I hope you guys have enjoyed this as much as I have. And I'm going to hop off of here soon and do some of these videos for you and get the Hey Scientist Mel 24/7 stream going. Thank you so much for being here, guys. And I'm sending you guys like super freaking squishy science hugs. If I can get back over to the screen. Ah, lovely, lovely, lovely technology. Hugs. I will see you guys next time.